Welcome to the Deep Dive, the show where we try to, cut through the noise and get straight to the real insights. If you've been following the whirlwind world of artificial intelligence, you know the story. It's often about just sheer breathtaking scale.
Right, this relentless pursuit of bigger, more powerful models. We hear about billions, sometimes even trillions, of parameters.
Exactly. And for a long time now, it's really felt like this arms race, you know, build the biggest machine. Because the thinking was, well, bigger is always better.
And that approach has undeniably given us some truly impressive results. Things like language understanding, content generation, amazing stuff. But it's also come with these huge costs, astronomical compute power, energy consumption, and maybe more importantly, it faces real challenges, especially when you talk about true, complex, multi-step reasoning.
Right. These massive models can sometimes stumble on the very kind of structured problem solving
Yeah.
that, frankly, we humans take for granted.
They really can, which makes you wonder.
Yeah, it makes me wonder, too, if this race for scale has these downsides, what other paths are there?
Mm.
Are we overlooking something maybe smarter, more efficient for getting to real intelligence? And that brings us to today. We're diving into a really fascinating new development, something that radically challenges this whole bigger is better idea. It's called the Hierarchical Reasoning Model, or HRM.
Okay, HRM. So what's the headline here?
Get this. Imagine an AI with only 27 million parameters. Now, put that in perspective. That's just a tiny, minuscule fraction of the multi-billion parameter giants we hear about every day.
27 million. Okay, that is small.
Right. But here's the kicker. It's achieving state-of-the-art results on complex tasks. Tasks where those massive models completely, utterly falter.
Wow. Okay, that definitely sounds counterintuitive.
Exactly. And that's precisely why we had to do a deep dive into it today.
Makes sense. So our mission today, then, is to really unpack this HRM. We need to look at its architecture. Sounds like it's brain-inspired.
Yeah, that's the claim.
Okay, so the architecture. We need to scrutinize its performance, especially against those top models on key benchmarks, and really try to understand what it means. What does it mean for such powerful performance to come out of such an ultra-small model?
And then look ahead, right? What practical use cases can we actually realistically expect from something like this, say, over the next year or two?
Exactly. Peering into the near future.
This deep dive, I think, really promises to flip some common assumptions on their head.
Oh.
So if you've ever felt maybe overwhelmed by the sheer scale of modern AI, or if you've wondered if there's a smarter, more efficient way to build truly intelligent systems, well, this deep dive is your shortcut to understanding what could be a paradigm-shifting development.
Yeah, you might find yourself having some serious aha moments here, thinking, wait, that's how it works?
Let's unpack this. So, okay, let's set the stage first. Talk about the current landscape. Large language models, LLMs.
Yeah.
They've undeniably achieved incredible success. I mean, they've revolutionized how we interact with information, how we generate text.
Oh, absolutely. They've shown remarkable proficiency across just a huge range of knowledge-based tasks. Summarizing articles, drafting emails, even coding assistants. They feel incredibly intelligent when you converse with them.
They really do.
Mm-hmm.
But there's always a but, isn't there? And the but here seems to be their true proficiency in complex multi-step reasoning, especially when it needs like a deep internal chain of logic. That still seems to be a pretty significant hurdle.
That's a really crucial distinction. LLMs excel at language tasks, sure. But their approach to complex reasoning, well, it often relies on something called chain of thought prompting. Kate.
Right, CoKT, that's where you tell it, let's think step by step or something similar.
Exactly. You're basically instructing the LLM to generate these intermediate linguistic steps. It's trying to make the model think out loud in text, kind of mimicking how a human might talk themselves through a problem.
It's a clever workaround, I'll give it that. And it has improved reasoning abilities in some cases.
No doubt, it was a significant step. But it's not without its fundamental weaknesses, pretty major ones, actually.
And those weaknesses really matter in practical applications, right? Like, for one, I understand CoT is incredibly brittle.
That's a huge one. Brittle is the perfect word. Think of it like a long sequence of dominoes. If just one falls incorrectly, even slightly off.
The whole process can derail.
Precisely. A single error in that generated chain of thought, maybe early on, can lead to a completely wrong conclusion, even if the model started out on the right track. And it doesn't really have a robust way to notice its mistake and backtrack or self-correct, not like a human might.
Okay, so brittleness is one. What else?
Well, it's also remarkably data hungry. To learn these reasoning patterns effectively, COTI approaches need vast amounts of training data, often meticulously structured data.
Which makes them expensive to develop and fine-tune for specific reasoning tasks.
Exactly. And then there's latency.
Yeah.
Generating those long, often very verbose chains of thought, well, that means more tokens, more computation, more time.
So it's slow.
It can be quite slow, yeah. Computationally expensive, which severely limits how useful they are in real-time applications where you need quick decisions. Think robotics or fast analysis.
Okay, that makes sense. The symptoms, brittleness, data hunger, latency, they're clear. But let's dig a layer deeper. What's actually going on inside these LLMs that makes them stumble on this fundamental reasoning problem? What's the architectural Achilles heel here?
Yeah, good question. Why do these massive models, even though we call them deep learning, struggle with something that seems so basic to intelligence?
Right.
Well, the core issue really lies in their fundamental architecture. LLMs are based on standard transformers, and transformers, despite having many layers, hence deep learning, are maybe paradoxically computationally shallow in a very specific technical sense.
Computationally shallow? How so?
It's about the fixed number of layers. This imposes a fundamental constraint on their effective computational depth. Think of it like this. A transformer processes all parts of its input sort of simultaneously, in parallel, within each layer. Then it passes the results to the next layer. It has many layers, yes, but each layer is effectively doing one pass over the data, maybe refining representations. But it's not really built for deep sequential iterative computation within a single pass.
Okay, I think I follow. So this architectural limit, what does it mean in terms of computational power?
Well, it places them in what computer scientists call lower computational complexity classes, things like AC0 or TC0. Now, without getting too technical, these are classes of problems that can be solved very quickly by parallel computers, but they don't typically include problems that require true iterative deep thinking or maintaining a complex state over many, many recursive steps.
So they aren't truly Turing complete end-to-end. They can't just compute anything a regular computer can.
Not end-to-end in a single forward pass, especially for tasks requiring things like unbounded loops or arbitrary memory access patterns inherent in complex algorithms. This is why they inherently struggle with tasks that need deliberate, multi-step planning or symbolic manipulation unless they externalize their thought process into language, like with COTIS.
They're not really built for deep, iterative internal computation. More like incredibly sophisticated pattern matchers and sequence predictors.
That's a good way to think about it, yeah. They're amazing at learning statistical patterns from data, but they're not inherently structured for the kind of algorithmic reasoning a human brain performs internally.
Okay, so if the current scaling approach with LLMs has these built-in architectural limits, what's the alternative? And this, I guess, brings us right back to the Hierarchical Reasoning Model, HRM. This sounds like a really significant departure from that bigger is better philosophy.
It absolutely is. HRM proposes a pretty fundamental philosophical shift. It moves away from that externalized token-level reasoning we see in COTIS.
Thinking out loud in text.
Right. It shifts towards what the creators call latent reasoning.
Latent reasoning. Okay, what does that mean exactly?
It means the complex, multi-step computations happen entirely within the model's internal hidden state space. It's like an internal dialogue, maybe, but one that never needs to be translated into human-readable language tokens at each step. The computation stays internal, latent.
That's a really intriguing idea. Latent reasoning.
Yeah.
How does that compare to, how our own brains work? We don't articulate every single micro step of our thought process out loud, or even consciously to ourselves, do we? A lot happens under the surface.
That's precisely the analogy they draw. A biological brain seems to execute these coherent chains of reasoning very efficiently in some kind of latent, probably non-linguistic space, without constantly translating back and forth to language. Language is maybe our primary tool for communicating thought, not necessarily the fundamental substrate upon which all thought occurs. And HRM sort of embodies this philosophy. It suggests that the very architecture of an AI model can itself serve as a powerful form of prior knowledge. Like, the structure itself gives it a strong inductive bias for reasoning, a built-in tendency or ability for problem solving.
Which is really different from the LLM approach, right? Where the idea is that these reasoning capabilities just kind of emerge statistically from seeing massive amounts of undifferentiated data.
Exactly. HRM suggests you can design for reasoning intelligence more directly rather than just hoping it pops out from sheer scale.
And what's really striking here, especially after we just talked about the limits of the giants, are the core claims made about HRM. I mean, when I first heard them, they almost sounded well, too good to be true.
They are indeed quite striking claims, claims that naturally and rightly invite skepticism. The introductory paper reports that this model, HRM, with only 27 million parameters.
Which, again, is just minuscule compared to GPT-4 or Claude 3 or Llama 3.
Right, a tiny fraction. And it's trained from scratch on just 1,000 examples.
1,000, not billions.
Right. 1,000 examples, with absolutely no pre-training whatsoever. And despite this, it achieves state-of-the-art and, in some specific cases, near-perfect performance on incredibly complex reasoning tasks.
Yeah, my first reaction when I heard that was healthy skepticism.
Yeah.
I mean, how? How can such a tiny model, trained on practically no data compared to the others, possibly outperform or even compete with these multi-billion parameter giants that have seen half the internet?
It seems to fly in the face of everything we've learned, doesn't it?
It really does. It directly challenges the scaling laws that, we've all kind of come to accept as gospel in AI development for the last few years.
And that skepticism is not only completely justified, it's widely shared in the research community. For years, these empirical scaling laws have successfully guided LLM development. They predict, quite reliably, that performance increases pretty predictably with model size, data, and compute.
Bigger plus more data plus more compute. Better performance. That's been the formula.
Basically, yes. And HRM's claims seem to just defy those laws. So questions immediately pop up. Can it genuinely scale beyond these specific tasks it was trained on? And crucially, can it generalize its reasoning capabilities to novel, unseen problems?
Right. The generalization question is huge.
It's critical, and this is precisely why it's so important to really dig into these claims, analyze the results, and understand the model's underlying architecture. Because if these claims hold up, even just for specific domains, it represents a really profound shift in how we might think about building intelligent systems.
Okay, so let's do that. Let's dive into the architecture. How exactly does HRM think in this brain-inspired, efficient way? What gives it this latent reasoning capability, especially given it's so small?
Right, so the efficiency and the reasoning power, the paper argues, come directly from its novel, brain-inspired architecture. It's fundamentally designed for a structured computational flow, one that enables deep, iterative reasoning within a single forward pass of the network, not just by stacking more layers or processing external language tokens.
Okay, so what's the core structure?
At its heart, it's a dual module system.
Dual module. Okay, tell us more. Is it like two specialized parts of a brain working together, each handling a different piece of the puzzle?
That's a perfect analogy. You can think of it as two interdependent recurrent modules, and they operate at different timescales, much like you might have different brain regions specializing in different kinds of processing.
Okay, so what are the two modules?
First, there's the high-level module, or H module. This acts as the slow planner.
The strategist.
Exactly. This module is responsible for devising the overall problem-solving strategy. It guides the reasoning process over a longer timescale. It operates at a relatively low frequency, and its main job is to integrate the results coming back from the low-level module to decide on the next major strategic step.
Okay, that sounds a bit like, Kahneman's System 2 thinking.
Yeah.
The conscious, effortful, deliberate processing we use for hard problems.
That's a very apt comparison. It's like the executive function setting the goals and monitoring progress.
Okay, so there's the slow planner, the H module. What's the other one?
The other is the low-level module, or L module. This is the fast executor.
Okay, the worker bee handling the details.
Precisely. The L module is the engine for the fast, detailed computations. It executes intensive search, refinement, local calculations for the subproblems that are defined and handed down by the H module.
And it operates faster.
Much faster. It operates at a high frequency. It performs multiple recurrent updates, multiple computation steps for each single update of the H module. This lets it rapidly explore a specific, confined part of the problem space, really digging into the nitty-gritty details.
So following the Kahneman analogy, this is more like System 1. The fast, automatic, intuitive stuff, the rapid subconscious calculations our brain does.
Yeah, that parallel works quite well. It's doing the rapid, intensive, localized work based on the directives from the higher level planner.
Can you walk us through an example? Like, how would this H module, L module dance play out in something concrete, like solving a tricky Sudoku puzzle? That seems to require both strategy and detailed checking.
Sure, Sudoku is a great example. So for a complex 9x9 Sudoku, the H module, the slow planner, might first look at the whole grid and establish a global strategy. It might decide, okay, the next strategic goal is to focus on filling the missing numbers within this specific 3x3 box in the top left corner, maybe because it has the fewest empty cells.
Makes sense. High-level plan.
Right. It passes this high-level goal along with the relevant context, the current state of the puzzle, down to the L module.
Okay, now the L module takes over.
Exactly. The L module gets this focused task. It then rapidly executes the local work, checking for possible number placements, identifying contradictions, maybe performing some constraint satisfaction only within that specific 3x3 box. It might internally run through multiple scenarios very quickly, performing many rapid iterative computations to see if it can uniquely determine a number for a cell or eliminate possibilities. This is where the intense search and refinement happens.
All happening internally, latently.
All internally. Once that subtask is complete, or maybe once the L module converges on a local solution, like, okay, based on the constraints in this box and the surrounding rice columns, a 5-foot must be placed in this specific cell, it then passes that refined local outcome, that piece of information, back up to the H module.
And the H module integrates that.
Yes. The H module takes that result, updates its overall understanding of the puzzle state. Okay, we now have a 5 here. And only then does the H module perform its slow update and set the next strategic goal. Perhaps it's, okay, now let's analyze the implications of that 5 for this particular row or column it sits in.
And this whole loop H module sets goal, L module computes intensely, L module reports back, H module integrates and sets next goal repeats.
Exactly. And this entire iterative loop happens entirely within the model's latent state. No need to generate text like, oh, okay, looking at the top left box, checking cell R1C1, can it be a 1? No. Can it be a 2? No.
Which makes it fundamentally more efficient and presumably less brittle than COTI,
Right.
which has to generate all those intermediate tokens.
Precisely. COTI has to externalize everything, which leads to the brittleness and latency we talked about. HRM keeps the reasoning internal and structured, allowing for much deeper and more efficient computation.
That interaction, that dynamic, sounds crucial. The higher level guiding and then resetting the lower level. This brings us to what the paper calls hierarchical convergence. How does that specifically enable this deep, sustained reasoning? Because older recurrent networks often had problems with computation just fizzling out, right?
That's right. This mechanism is really key because it directly addresses a long-standing limitation of traditional recurrent neural networks, RNNs. Older RNNs, while designed for sequences and internal state, often tend to stall computation. Their internal state updates can quickly converge towards a fixed point, meaning the magnitude of changes shrinks rapidly, sometimes exponentially.
So they basically stop learning or processing effectively after a few steps, like trying to think deeply, but your thoughts just fade into a static hum.
That's a good analogy. Their internal state settles down too quickly, which effectively caps the network's useful computational depth. HRM's architecture, with this hierarchical structure, elegantly sidesteps this very problem.
Okay, so how does it avoid getting stuck in that rut? How does it maintain that dynamic internal activity needed for complex problems?
It does it through this beautiful nested loop of computation that keeps things dynamic and deep. Let's trace it again. 1, the H module provides its high-level state, establishing a context or a goal for the L module.
Okay, sets the scene.
2, the L module then performs multiple rapid recurrent steps. It efficiently computes and converges towards a local equilibrium, a stable state conditioned on that specific context given by the H module.
Yeah.
It solves its specific subtask and stabilizes its local solution.
Right, finds the answer for its little piece of the puzzle.
3, crucially, after the L module finishes its subcomputation and reaches that local equilibrium, the H module incorporates the outcome. And then the H module performs its single slow update based on that new information. 4, now here's the magic. That update to the H module state does something vital. It establishes a fresh context for the L module. It changes the landscape, so to speak. This effectively restarts the L module's computational path, kicking off a new phase of convergence toward a different local equilibrium, now conditioned on the updated global state from the H module.
Ah, I see. So the H module's update essentially gives the L module a new starting point, a new sub-problem to chew on, preventing it from just settling down and staying there. It keeps resetting the computation.
Exactly. It's like a constant reinitialization of the local problem space for the fast module, preventing it from ever truly stalling out.
That sounds incredibly efficient for problems that need many steps, like planning or that Sudoku example.
Precisely. This nested loop allows HRM to perform a sequence of distinct, stable, and potentially incredibly deep computations. While a standard RNN's computational activity might rapidly decay, HRM can maintain high activity over many, many effective steps because the H module keeps nudging the L module onto new computational paths with fresh contexts. This gives HRM an effective computational depth that can be thought of as n times t steps, where n is the number of slow H module cycles and t is the number of fast L module steps it takes within each cycle. This dynamic allocation of computation over time is fundamentally different from fixed depth transformers. It allows HRM to achieve a depth far greater than models with just a set number of layers.
And that's how it tackles problems requiring long horizon planning and stateful iterative refinement with such high accuracy, even with so few parameters.
It's the core architectural insight, yes.
Okay, fascinating. Now, from an implementation standpoint, how is this actually built? Are we talking about some completely new type of neural network block we've never seen before?
No, actually, and that's another really ingenious aspect of the design. Both the H and L modules are implemented using pretty standard encoder-only transformer blocks. They leverage the power of the attention mechanism, which we know works well, for their internal computations.
So it's not entirely new building blocks, but a novel arrangement and interaction of existing, well-understood ones.
Exactly. It's clever architecture, not necessarily inventing brand new primitives. What is innovative, though, are the training techniques they use to make this whole recurrent hierarchical structure stable and efficient to train.
Like what?
Well, they use a technique called one-step gradient approximation. This simplifies the complex math needed to train recurrent networks over many steps, avoiding the full complexity of traditional backpropagation through time, or BPTT. They also use something called adaptive computation time, or ACT.
ACT, what does that do?
ACT basically allows the model to dynamically decide how many computational steps, how many of those L module updates to take for each input or each H module cycle, rather than having a fixed number. It can spend more thinking time on harder parts of the problem.
Ah, so it adapts its effort. That sounds efficient too.
It is. And together, these techniques enable stable and efficient training without relying on the full, computationally expensive, and often unstable BPTT algorithm, which is typically a headache for training recurrent systems over long sequences. This approach significantly cuts down on memory usage and the overall compute needed for training.
Which makes it cheaper and faster to train these models.
Considerably so, yes. And importantly, in a move that really helps the research community, the creators at Sapient Intelligence have made the code publicly available on GitHub. It's under a permissive Apache 2.0 license, and they've also released trained checkpoints.
That's great. Transparency is huge for letting others verify the results and build on this work.
Absolutely. It's a big deal for fostering more research in this architectural direction.
Okay, so we've got the philosophy, latent reasoning, we've got the architecture, dual modules, hierarchical convergence. We know how it's built and trained. Now, let's get to the brass tacks, performance. Where does HRM truly stand out, especially when you stack it up against the Goliaths of the AI world?
Right. This is where HRM's claims become really compelling and really illustrate its unique strengths. Its most unambiguous success, the place where it clearly shines, is its reported nearly perfect performance on complex, closed-world, algorithmic, and symbolic puzzles.
Closed world, meaning problems with clear rules and definite answers.
Exactly. Think logic puzzles, constraint satisfaction, pathfinding. These are the kinds of tasks that demand precise, step-by-step reasoning, maintaining state accurately over many steps, and often exploring vast search spaces. And these are exactly the areas where traditional LLMs, even the biggest ones, fundamentally struggle.
Can you give us some specific benchmarks mentioned in the paper that really highlight this difference?
Absolutely. The paper focuses on two key examples that are designed to be hard. First, Sudoku-Extreme. These aren't your typical newspaper Sudoku puzzles. They're difficult 9x9 grids selected specifically because they require extensive tree search and backtracking capabilities to solve reliably.
So really tough logic puzzles.
Very tough computationally. The other key benchmark is maze hard. This involves finding the optimal, shortest path in large, complex 30x30 mazes. Again, this requires precise pathfinding over a large state space, keeping track of visited nodes, potential paths, and so on.
And how do the big LLMs do on these?
According to the HRM paper and related research, state-of-the-art LLMs, even when using advanced chain-of-thought prompting techniques, have been shown to completely fail on these specific hard versions. They either get stuck partway through, make critical logical errors, loop indefinitely, or simply cannot find the optimal solution within practical computational limits.
And the reason for that failure, again, loops back to their architecture, right?
Yeah.
Even trying to think step by step with Coty, they just can't maintain the necessary state or perform the deep search needed.
Exactly right. That fixed computationally shallow depth of standard transformers just prevents them from effectively maintaining the complex state required across numerous steps. They can't efficiently explore the vast search spaces inherent in these problems. Research has shown that increasing a transformer's depth can marginally improve its performance on something like Sudoku, but it quickly saturates at a level far, far from optimal. It's just not the right tool for the job.
But HRM, with its hierarchical structure.
HRM, on the other hand, leverages that deep computational capacity enabled by hierarchical convergence, the H module repeatedly resetting the L module's focus, allowing for that deep, iterative NXT computation. And the result? The paper reports near-perfect accuracy on both Sudoku-Extreme and Maze-Hard.
Wow. Near perfect.
Which provides really strong, pretty undeniable evidence that for this class of structured algorithmic reasoning tasks, HRM's architecture is fundamentally more capable and vastly more efficient than that of standard LLMs. It's not just a little bit better. For these specific kinds of problems, it's truly a night and day difference.
Okay, that really drives home the point about its specialized power. Now, there's another benchmark that always comes up in these AI capability discussions, the Abstraction and Reasoning Corpus, ARC-AGI. It's often seen as a measure of something closer to general intelligence. How does HRM do there? I know there was maybe some confusion around the reported numbers.
Yes, ARC is definitely a benchmark that gets a lot of attention.
Yeah.
It was created by Francois Chalet, and it's designed specifically to measure what he calls fluid intelligence.
Fluid intelligence.
Yeah, basically the ability to figure things out on the fly. ARC tests an AI's ability to look at just a few examples of a completely novel abstract puzzle, grasp the underlying pattern or rule, and then apply that rule to solve a new instance of the puzzle. The key thing is that it's designed so you can't just memorize solutions or pre-prepare for the specific tasks. Each task presents genuinely new logic.
So it's really testing on-the-fly skill acquisition and generalization, not just pattern matching on stuff it's seen before.
Exactly. And this unique design makes the context of how HRM was evaluated on ARC really important.
Okay, so what were those scores that were reported, and what was the source of the confusion?
Well, initially, a score of 40.3% accuracy on the main ARC-AGI benchmark was reported. This was achieved by HRM after being trained from scratch, specifically on the official ARC training dataset, which consists of about 1,000 examples provided by the challenge itself.
Okay, 40.3%, trained on the ARC data.
Then a figure of 55.0% on a variant called ARC-AGI2 also appeared in a bar chart in an early preprint labeled as a self-reported score. However, later press releases from Sapient Intelligence cited a much more conservative score of 5% on ARC-AGI2.
Okay, wait, 40%, 55%, 5%. That's a pretty significant spread. It's frankly a bit confusing if you're trying to understand its true capability on ARC. What's the critical caveat here? What helps us make sense of this?
The most significant point of discussion, and the critical caveat, particularly for that higher 40.3% score, is the methodology. By training the model directly on the ARC dataset itself, the very examples that make up the benchmark, it fundamentally deviates from ARC's core philosophy.
Which is testing generalization to entirely novel tasks.
Right. The benchmark is intended to test zero-shot or few-shot generalization, where the model sees maybe a couple of examples of a new task type right before solving it, but hasn't been explicitly trained on the logic of the test tasks beforehand.
So while training on the ARC data and getting 40% is maybe an incredibly powerful demonstration of HRM's sample efficiency, its amazing ability to learn complex rules from just 1,000 examples.
Which it absolutely is. That sample efficiency is remarkable in itself.
It means that 40.3% score can't be directly compared to the performance of other models that are evaluated in the intended unprepared manner. That is, models tested on tasks they've truly never seen before during training.
Precisely. It's impressive that it can learn those complex ARC patterns from so little data, showing incredible data efficiency, but it's not quite solving ARC in the way the benchmark is usually interpreted in the context of AGI research, which is all about that zero-shot or few-shot generalization to unseen problem types.
Okay, so how do we contextualize the other numbers then, like the 5%? How does that compare to how other leading models perform on ARC when evaluated correctly?
Well, when leading LLMs are evaluated correctly in a few-shot setting, where they get a few examples of the task logic just before trying to solve it but haven't been trained on the test set, they typically score much lower than that 40%. For instance, baseline few-shot evaluations Often place models like GPT-4o and Google's Gemini 1.5 Pro somewhere in the 5% to maybe 9% accuracy range. Anthropic's Claude 3.5 Sonnet has shown higher scores, reportedly in the 14% to 21% range, using similar few-shot methods.
So that more conservative 5% score reported later for HRM actually aligns it pretty squarely with these massive state-of-the-art models when it's evaluated under those stricter, more comparable few-shot or unprepared conditions.
Exactly, and that's where the radical efficiency story really shines through again, isn't it?
Yeah, absolutely. To be performing in that same ballpark as GPT-4o or Gemini 1.5 on a task like ARC, which is designed to be hard even for humans,
Yeah.
but doing it with only 27 million parameters and zero pre-training, that's astounding.
It really is. The crucial distinction, the key takeaway for you, is that HRM achieves this comparable level of fluid reasoning, that ability to tackle novel abstract tasks on the fly with just a tiny fraction of the parameters and without any of the massive pre-training on generalized data sets that those other models rely on.
So it reframes the contribution. It's not necessarily a magic bullet AGI that solved ARC in the most general sense with that 40% score, but rather it's an extremely efficient and architecturally superior system for learning and executing algorithmic tasks, even complex abstract ones, from very limited examples.
Precisely. It demonstrates powerfully that with the right purpose-built architecture, you can achieve remarkable reasoning performance with minimal resources. It's a testament to architectural ingenuity over brute force scale for these kinds of tasks.
Okay, so just to give our listeners the full picture from the source material, let's quickly run through that comparison table again for ARC AGI performance, keeping the context in mind. HRM at 27M parameters shows 5.0% using an unspecified or likely few-shot method. That puts it right alongside GPT-4o, also at 5.0% using baseline few-shot, and Gemini 1.5 Pro at 4.5% baseline few-shot. Claude 3.5 Sonnet seems a bit higher, between 14% and 21% baseline few-shot.
All massive models, mind you.
Right, all giants. And then there's this outlier, Llama 3.1, a 405 billion parameter model, reportedly scoring 96.9% on the ARC challenge. Though, as the sources note, this number is exceptionally high, even compared to average human performance, which is around 64%.
Yeah.
So it likely needs more independent verification regarding the exact methodology used.
Yeah, that llama number definitely stands out and needs a closer look. But setting that aside, the key point remains. HRM, tiny, no pre-training, is playing in the same league as the biggest pre-trained models on this fluid reasoning task when compared fairly. That radical efficiency is the headline. It really shifts the conversation from just scale to intelligent design.
It really is something. But it also begs a pretty obvious question. If it's so good at these specialized reasoning tasks like Sudoku, mazes, and even learning ARC patterns efficiently, why don't we see performance numbers for it on the standard general LLM benchmarks? You know, things like MMLU for general knowledge, GSM-8K for math word problems, or HumanEal for code generation. Those are the tests we usually see for leading AI models.
That's a very astute observation, and it's definitely not an oversight in the HRM paper or its positioning. The absence of performance data on those broad general benchmarks actually reflects HRM's fundamental nature and its design philosophy. Meaning it's simply not designed to be a generalist knowledge engine or a fluent conversationalist that can chat about any topic under the sun. It completely lacks the massive pre-training on diverse text and code corpora, literally billions upon billions of words, articles, books, websites, lines of code, that is absolutely necessary to build the vast world knowledge, common sense, and nuanced linguistic capabilities tested by benchmarks like MMLU or GSM-8K.
So it just doesn't know things in the way an LLM does. It doesn't have that broad understanding of the world embedded in its parameters.
Exactly. It wasn't trained for that. It hasn't read Wikipedia or coded millions of GitHub repos. Its evaluation, therefore, has to be viewed through the lens of what it is, a pure, specialized reasoning architecture.
So it's not a jack of all trades, master of none. It's a master of one very specific, very important domain, structured, iterative, algorithmic reasoning. It sounds like a highly optimized computational engine built for a narrow but deep set of problems.
That's a perfect way to describe it. It's not trying to replace a general-purpose LLM across the board. It's designed to solve a specific, challenging problem that LLMs demonstrably struggle with, the kind of problems that require methodical, multi-step logical deduction, complex search, or precise symbolic manipulation, rather than broad factual recall or fluent language generation.
Okay, this understanding of it as a specialist, not a generalist, really leads us into a much broader discussion about the strategic significance of models like HRM. It feels like this is directly challenging the AI orthodoxy we've kind of lived with for the past few years,
Yeah.
almost upending the established rules of the game.
It absolutely feels that way. For what? The better part of a decade now, AI progress, especially in language and vision, has been heavily guided by these empirical scaling laws.
Right. The idea that performance just gets better and better if you throw more data, more compute, and bigger models at the problem.
Exactly. These laws, first observed maybe in simpler models and then famously documented for transformers, reliably predicted that a model's performance improves pretty smoothly, often as a power law function of its size, the dataset size, and the compute used for training. This seemingly universal principle has driven this massive industry-wide race to build ever larger models, leading us to today's multi-trillion parameter behemoths.
The scale is all you need, philosophy, essentially.
That phrase captures it perfectly. And while it's yielded impressive results, as we said, it also comes with those astronomical costs, huge energy demands, and, maybe critically, it tends to centralize power. It puts cutting-edge AI development primarily in the hands of a few large organizations that have access to the necessary massive computational resources and proprietary datasets. It creates a kind of bottleneck for innovation.
And HRM then lands like a powerful counter-narrative to this scale is all you need idea. It demonstrates there might be another, perhaps more intelligent way forward.
Precisely. HRM serves as a really potent argument against that seemingly ironclad principle, at least for certain domains. It demonstrates that for critical areas, particularly this kind of deep algorithmic reasoning, architectural ingenuity, clever design can deliver what feels like a step function improvement in capability. A jump that breaks away from that smooth, predictable curve of just scaling up the same old architecture.
So it makes a compelling case that a superior architecture, one with strong inductive biases tailored to the type of problem you're trying to solve, can be a more effective and vastly more efficient path to intelligence than just blindly increasing the scale of a general-purpose one.
That's the argument it puts forward, yes. And if that holds true, it radically alters the crucial equations. Performance per watt, performance per dollar. It fundamentally shifts the competitive focus in AI, maybe away from just a capital-intensive scramble for ever larger supercomputers towards a more talent-intensive pursuit of clever architectural innovation. It potentially widens the playing field quite dramatically.
That shift has huge economic and strategic implications, doesn't it? It could genuinely democratize advanced AI capabilities, lowering those incredibly high barriers to entry we just talked about.
Absolutely. The economic side of this is profound. By showing that you can achieve powerful reasoning without needing those massive pre-training runs that cost millions of dollars and require tens of thousands of GPUs running for months, well, HRM dramatically lowers the financial and computational hurdles for developing and deploying advanced AI.
Which could unleash a lot more innovation.
Potentially, yes. It could democratize capabilities that were previously almost exclusive to a handful of tech giants. Imagine the difference for, say, a university research lab or a smaller startup. The difference between needing access to a multi-million-dollar supercomputer cluster versus potentially being able to train a highly capable reasoning model on just a handful of high-end GPUs, maybe even on a powerful desktop workstation.
So smaller companies, academic labs, maybe even dedicated individuals or specialized research groups could realistically train and run sophisticated reasoning models without needing enormous budgets or venture capital funding. That feels like a true game changer for innovation.
It really could be. It fosters the potential for a much more diverse, competitive, and perhaps ultimately more innovative ecosystem. You could see, as some are speculating, a kind of Cambrian explosion of specialized AI startups. Companies focusing intensely on solving specific niche problems in vertical industries, think optimizing complex logistics routes in real time, accelerating drug discovery by reasoning through molecular interactions, designing novel materials with specific properties.
Using custom-trained, highly efficient models tailored for that exact task.
Exactly. Moving away from a complete reliance on just consuming expensive general-purpose APIs from a few large providers and opening up new avenues for highly specialized, efficient solutions.
This also seems to point towards a different kind of future for AI architecture itself. Maybe not one giant monolithic AI brain trying to do everything, but rather maybe a collection of specialized experts working together, a federation of specialists, as I've heard it called, kind of like how different regions of our own brain handle different cognitive functions.
Oh, that's an excellent way to put it, and I think HRM's specialized nature strongly points in that direction. It suggests a future AI architecture that isn't necessarily a single monolithic system, but rather a more hybrid modular system.
How would that work in practice?
Well, you could envision a large language model, a GPT-4, a Claude 3, a Llama 3 serving as the broad knowledge base and the primary user interface. It excels at understanding natural language, generating creative text, accessing vast amounts of factual information, holding a conversation.
Okay, the front end, the generalist.
Right. But then when a task comes along that requires deep, structured, or algorithmic reasoning, maybe it's a complex Sudoku puzzle embedded in a user's request, or a precise financial modeling calculation, or an intricate logistics optimization problem, or even debugging a tricky piece of code, the LLM could recognize that need.
And instead of trying to brute force it with chain of thought.
Instead of struggling with Kotao, it could seamlessly offload that specific demanding reasoning task to a highly efficient, specialized coprocessor, a module built on an HRM-like architecture designed specifically for that kind of deep computation.
Like delegating to an expert colleague.
Exactly. So you'd get the best of both worlds. You leverage the vast knowledge and the linguistic fluency of the LLM, but you combine it with the deep, efficient, and potentially much more reliable reasoning capabilities of these purpose-built architectures for the tasks they excel at.
That sounds like a much more robust path towards more capable AI, maybe even more biologically plausible, mirroring that functional specialization and interconnectedness we see in the human brain.
That's the vision it suggests, yes. That complex intelligence might emerge not just from ever larger, undifferentiated networks, but from elegantly designed, specialized components working together in a synergistic complementary fashion, each part contributing its unique strength to the whole system, leading to overall capabilities that might exceed what any single monolithic system could achieve on its own.
This is genuinely exciting stuff. Okay, so looking ahead now, let's talk applications. Given HRM's unique profile, small, fast, data efficient, strong on reasoning, what are the projected applications? Where do you see this type of technology making a real-world commercial impact in say, the next 12 to 24 months? What use cases can we realistically expect to see taking shape?
Yeah, that's the crucial next step, isn't it? Moving from research breakthrough to real-world value. Given HRM's unique characteristics, it seems ideally positioned for significant impact in specific high-value domains that are often outside the traditional realm of consumer-facing chatbots or general content generation.
Okay, so where's its natural home?
Its most promising near-term ecosystem looks like edge AI, robotics, and the broader Internet of Things, or IoT space.
Edge AI meaning running the AI directly on the local device, right? Not relying on sending data back and forth to a big cloud server for all the thinking.
Exactly. And this seems like the perfect fit for HRM. Think about the core benefits of edge AI. You get reduced latency, which means faster real-time responses. You get enhanced data privacy and security because sensitive data doesn't have to leave the device. You get lower bandwidth consumption, sending less data over networks. And critically, you get the ability for the device to function intelligently even when it's offline or has intermittent connectivity.
And HRM's features map directly onto those benefits.
Perfectly. It's like bringing a powerful reasoning brain directly to the device itself.
So HRM's incredibly small footprint, that 27 million parameters, reportedly under 200 millimeter of RAM needed. That means it can run on almost anything with a chip, right? Not just powerful servers.
Pretty much. It's small enough to be deployed on highly resource-constrained hardware. Think about the embedded systems already present in industrial machinery on a factory floor, or the advanced driver assistance systems, ADS, in modern cars, or maybe even portable medical diagnostic devices.
And it's low latency. That's critical for real-time stuff.
Absolutely. The fact that it performs complex reasoning potentially within a single, very fast-forward pass is crucial for real-time applications. Think about a robot navigating a cluttered, dynamic warehouse floor. It needs to make decisions instantly. Or an autonomous vehicle reacting to a sudden obstacle, no time to wait for a round trip to the cloud.
And the privacy angle you mentioned seems huge too, especially in industrial or medical settings where data sensitivity is paramount.
Definitely. By processing data locally, right there on the device, highly sensitive information like patient health data from a portable scanner, or proprietary factory production metrics from industrial sensors, or even personal user data on a smart home device never needs to be transmitted over a network. It stays local. This significantly mitigates risks of data interception breaches and helps ensure compliance with strict data sovereignty regulations like GDPR or HIPAA. It enables privacy by design.
And don't forget the data efficiency. Training on just 1,000 examples. That must open doors where data is scarce.
That's another game changer. The ability to potentially train a powerful reasoning model on such a small data set, without needing massive pre-training on general web data is huge for specialized industrial and medical applications. In these fields, large, well-labeled data sets are often simply unavailable, or they're prohibitively expensive and time-consuming to create. Or maybe the phenomena you're studying, like rare diseases, just don't generate large data sets. HRM offers a path forward there.
Okay, so let's connect these unique advantages, small size, low latency, privacy, data efficiency, to specific high-value use cases we might actually see emerging within the next 12 to 24 months. Where will HRM-like models really start to shine in the real world soon?
Within that near-term time frame, I think we can anticipate development efforts using architectures like HRM to focus intensely on several key areas. First, definitely industrial IoT and predictive maintenance.
Okay, how would that work?
Imagine deploying HRM directly onto sensors attached to critical machinery and factory sensors, monitoring real-time vibration, temperature, acoustic signals, energy usage. The HRM model, running right there on the edge, could perform complex on-device reasoning to analyze those sensor streams and predict potential mechanical failures before they happen.
Ah, predicting breakdowns to optimize maintenance schedules.
Exactly. Optimizing machine uptime, preventing costly unexpected downtime. It could also potentially analyze manufacturing processes in real time to spot inefficiencies or automate quality control checks right on the production line, all without sending sensitive proprietary operational data offsite to the cloud. That keeps the manufacturer's data secure.
That sounds like a massive leap in efficiency and security for manufacturing. Yeah. Could save companies enormous amounts of money.
Absolutely. Another critical near-term area is robotics and autonomous systems.
Makes sense given the need for real-time onboard decisions.
Precisely. HRM, or something like it, could serve as the on-device decision brain for next-generation robots and drones. This could enable autonomous systems to better perceive their environment, understand complex instructions, and perform sophisticated multi-step tasks. Think beyond simple pick and place to things like, okay, robot, pick up the red box from that shelf, carefully place it inside the waiting blue container over there, and then navigate past that moving forklift to reach the charging station.
Tasks that require planning, state tracking, and real-time adaptation.
Yes, all using local computation for speed and reliability. This is vital for applications ranging from logistics and automated warehousing to agricultural robotics, infrastructure inspection, and maybe even more capable consumer robots down the line.
And you mentioned earlier its creators are also looking into healthcare applications. That seems incredibly promising, especially given the data efficiency aspect for rare conditions.
Yes, the source material indicates partnerships are actively being pursued in healthcare and medical diagnostics. HRM's remarkable data efficiency, combined with its capacity for deep deductive reasoning, makes it potentially uniquely suited for complex diagnostic challenges, particularly for rare diseases where you might only have a handful of documented cases or subtle, complex patterns in medical images or sensor data.
So it could potentially reason from those subtle signals within a very limited data set to suggest potential rare diagnoses or maybe even optimal treatment pathways, performing the kind of nuanced, logical inference that maybe even human experts struggle with given data scarcity.
That's the potential, yes. It could be a powerful tool to augment clinical decision-making in those really challenging data-sparse scenarios. It's a very high-value, high-impact application area they seem to be targeting.
Incredibly impactful, potentially offering hope where diagnosis is currently extremely difficult. Are there any other notable areas where it might make a near-term splash?
One more area highlighted is climate and scientific modeling. The model reportedly achieved very high accuracy, 97%, on a specific climate forecasting task mentioned in their materials.
Interesting. So modeling complex systems.
Yes, it highlights its potential for modeling complex dynamic systems where you need to perform iterative refinement and understand long-range dependencies over time. This could apply to predicting weather patterns, ocean currents, the spread of wildfires, or maybe even simulating complex chemical reactions or biological processes. It shows its versatility might extend beyond just structured puzzles into the realm of scientific simulation and discovery.
Okay, so just to quickly recap that strategic mapping from the source material, showing how HRM's specific advantages translate directly to these near-term applications. Its small parameter count and low memory footprint, 200mm RAM, mean it runs on constrained hardware, like in-car systems, potentially predicting traffic hazards locally. Its low latency enables real-time decisions crucial for robotics, like high-speed sorting robots in a warehouse. Its high data efficiency, training on maybe just 1,000 samples, makes it ideal for medical diagnostics, reasoning effectively over limited patient data for rare diseases. And its inherent privacy, Keeping computation on device is critical for industrial IoT, analyzing proprietary factory data securely without it ever leaving the premises.
That nails it. Those are the key advantages directly aligning with these critical, high-value applications where we expect to see significant development activity leveraging HRM-like architectures in the next year or two.
It really sounds like a potential runaway success, possibly transformative across several industries.
Yeah.
But it can't be entirely smooth sailing, can it?
Yeah.
What are the hurdles? What challenges need to be overcome for widespread adoption, even in these specialized areas?
You're absolutely right to ask that. No technology is a silver bullet, and HRM is no exception. There are definitely several practical hurdles that need to be addressed before we see widespread adoption. The first, and maybe most significant, is its specialist nature, which we've discussed. HRM is fundamentally not a general-purpose tool.
Meaning you have to train it specifically for each new task.
Exactly. Deploying it effectively for a new reasoning problem requires effort. You need to curate a training data set, even if it's small, just as an examples, that's specific to that task. And then you need to run a dedicated training process for that specific application. It's not like an LLM where you can often just prompt it for a new task.
Yeah.
HRM requires deliberate task-specific training. It's not plug and play for everything.
So that means for applications that really need a blend, say, deep reasoning combined with broad world knowledge or fluent natural language interaction with the user, HRM isn't enough on its own. It really needs that partner, that hybrid approach.
Precisely. Its inherent lack of generalist capabilities means that for those kinds of blended applications, a pure HRM model is insufficient. This strongly reinforces the need for those hybrid architectures we talked about, where it acts as a specialized coprocessor alongside an LLM.
But that modularity, while powerful, also brings its own challenges, right? Like integration.
It does. Integrating these different types of models seamlessly presents engineering challenges. Furthermore, the current publicly available code for HRM is primarily geared towards research. There is still significant engineering effort needed to transform that research code into a robust, scalable, easily integrable commercial software development kit, SDK, or perhaps a full end-to-end product that can be readily adopted by diverse industries with different needs and existing infrastructure. It's a classic research breakthrough that now needs serious productization effort.
Makes sense. Research code isn't production code. Are there any other concerns, maybe around stability or reliability, especially given how small and efficient it is, and that it's trained on those very tiny data sets?
Yes, that's another point raised in the project's own documentation. They note potential risks of late-stage overfitting, where the model learns the small training data set too well and loses generalization ability, and also potential numerical instability issues when training on exceptionally small data sets.
So while its data efficiency is a massive strength, it also requires careful handling.
It seems so. It means careful management during the training and validation process is necessary. This might involve techniques like rigorous testing, cross-validation, and perhaps using methods like early stopping during training, stopping before it overfits too much, to ensure that the deployed systems are reliable and robust enough for real-world mission-critical applications. So while it's incredibly powerful and efficient, it's not entirely without its operational considerations and likely requires skilled AML engineering to deploy dependably in production.
Okay, that gives us a balanced picture. So let's try to synthesize all of our findings from this deep dive today. The Hierarchical Reasoning Model, HRM, it feels like much more than just another incremental AI model release. It really stands out as a landmark proof of concept, doesn't it? One that fundamentally challenges some core assumptions that have guided modern AI development, particularly the overwhelming dominance of the scaling laws.
I think that's exactly right. HRM's primary contribution, the headline story, is its radical efficiency. By leveraging this novel, brain-inspired, dual-module recurrent structure, and particularly that clever hierarchical convergence mechanism, it achieves a level of performance on complex symbolic and algorithmic tasks that seems demonstrably intractable, or at least vastly less efficient for even the largest language models. It truly excels as a highly proficient specialist reasoning engine.
But it's equally clear from our discussion and the source material that it's not a generalist knowledge engine. It's not here to replace LLMs for tasks that require accessing vast stores of world knowledge, applying common-sense reasoning across broad domains, or engaging in nuanced, creative linguistic interactions. Its triumph isn't in universality, but in its profound mastery of a specific critical domain of intelligence, that deep, iterative, structured problem solving.
And this distinction, this specialist nature, leads us directly to what seems like the most promising future for HRM and the architectural ideas it represents. It's likely not as standalone, all-encompassing AI solutions, but rather as essential integrated components within larger, perhaps disaggregated AI systems.
The hybrid model.
Exactly. Today's LLMs are incredibly powerful knowledge bases and natural language interfaces, but they possess this notable bottleneck, this Achilles heel, when it comes to deep, stateful algorithmic reasoning.
So an HRM-like module could slot right into that gap, functioning almost like a dedicated reasoning coprocessor within a larger system. Seamlessly integrated with an LLM, ready to handle the complex logical, spatial, or algorithmic tasks that get passed to it, almost like the LLM delegating a tough calculation or a planning problem to an internal specialized expert.
That looks like a really powerful and plausible path forward. This hybrid federation of specialists model offers a potentially more robust, efficient, and maybe even more reliable approach to building increasingly capable AI. It's about combining the distinct strengths, the incredible breadth and fluency of LLMs with the deep, efficient, and reliable reasoning of purpose-built architectures like HRM to overcome the individual weaknesses of each approach.
This whole development truly forces the AI community, and really us as informed observers trying to understand this field, to reconsider the primary path we've been on towards more capable intelligence. What does this shift, this focus on architecture over sheer scale, mean for innovation, for accessibility, for the very nature of AI itself? It really suggests a future where intelligence isn't necessarily a monolith, but maybe a complex, elegant tapestry woven from specialized capabilities.
It's a profound question, and one definitely worth pondering as we track developments in this area. Perhaps the future of AI won't ultimately be defined solely by how big we can build our models, but increasingly by how smartly and elegantly we can design their architectures. This could lead to a new era of highly efficient, specialized, and truly intelligent systems that are far more effective at solving specific, critical, real-world problems.
A powerful thought to leave you with. Thank you for diving deep with us today on The Deep Dive. We really hope you found some serious insights and perhaps even a fresh perspective on the fascinating, rapidly evolving future of artificial intelligence through this look at HRM.